10.2 Arcs and Chords. We're going to learn to use properties of arcs of circles and use properties of chords of circles. So here we go. A few terms. A central angle. Remember, a central angle is an angle whose vertex is on the center of the circle. Angle ACB is a central angle because angle ACB has its vertex C on the center of the circle. A minor arc. A minor arc, remember, is a part of a circle that measures less than 180 degrees. A diameter, remember, passes through the center of a circle, cuts the circle exactly in half. All the way around the circle, remember, is 360 degrees. Halfway around a circle is 180 degrees. A minor arc, then, would be less than half of a circle. There are several minor arcs in this diagram. There's an arc here, arc AB. When you name an arc, you use the arc symbol and its beginning and ending points. Remember, for a minor arc, we need just two letters, so for this arc, we would call it arc AB. There's other minor arcs. Here's another one. We'd call this arc, arc EA. Direction doesn't matter. You could also call it arc AE. Be the same name for that arc. Just need the two endpoints. Okay. There are a few other arcs in this example that we could name, but let's just move on to our next term. A major arc. A major arc is a part of a circle that measures between 180 and 360. So it would be more than 180 degrees and less than 360. There's an arc on this side of our circle that fits that description. But I have to be careful what we name it. If we were to name it just arc AB would not be the major arc. Arc AB would be the minor arc here between A and B. So how can we name the other side of the circle? Well, to name the other side of a circle, what we need is another point on the circle, and then use three letters to name that arc. So if we want to name this arc the major arc, the arc more than 180 degrees, we would need its beginning point and its ending point, and then one other point in between to tell us what direction to go, so that we know not to go just straight from A to B. That would be the minor arc AB. But we want to go all the way from A around towards F and then ending at B, so that we're naming the major arc AFB. A semicircle. A semicircle is an arc whose endpoints are the endpoints of a diameter. When naming a semicircle, again, we would need three letters, because if we just said arc AB, students wouldn't know if we're talking about the upper half of this circle or if we wanted the lower half of this circle. So when naming this arc, we need some other letters. To name our semicircle, we need some other letters on the circle. So we can put, maybe a C here, put a D down here. And if I said arc ACB, then you would know I was speaking about the top half of the circle. If I were to say arc ADB, then you would know we were speaking about the lower half of the circle. So, semicircles and major arcs, we need three letters to name the arc. The measure of a minor arc. The measure of a minor arc is the same as the measure of its central angle. So if I wanted the measure of arc AB, the measure of this arc would be the same as the measure of this angle. If angle ACB is a 50-degree angle, if angle ACB equals 50 degrees, then arc AB equals 50 degrees. The measure of a minor arc is the same as the measure of its central angle. Remember, a central angle is an angle whose vertex is on the center of the circle. To find the measure of a major arc. To find the measure of a major arc, you would find the difference between 360 degrees and the measure of its associated minor arc. Remember that the degree measure of an entire circle all the way around the circle is 360 degrees. So if I wanted to find the measure of, let's say, arc AFB, I would first need to know the measure of the angle ACB. Let's use that 50 degrees again that we used before. If angle ACB is 50 degrees, and I want to find the measure of arc AFB, then I would take the measure of the entire circle minus the measure of this portion of the circle that we're not using, and what remains would be the arc that we're looking for, 310 degrees. So, to find the measure of a major arc, take the difference between 360 degrees and the measure of its associated minor arc. The arc addition postulate. Sometimes, to find the measure of an arc, we may need to add two or more arcs together. For instance, if I wanted to find the measure of the arc ABC, that would be an arc beginning at A, going towards B, and ending at C. To find the measure of this arc, then, I would add arc AB plus arc BC. So, sometimes you may have to add two or more arcs together to find the measure of the arc that you're looking for. Well, let's look at a couple of examples. In example 1, we want to find the measure of arc DG. So we want to begin at D and move around to G. So we need to add arc DF plus arc FG, or an 80-degree arc plus a 70-degree arc, for a total of 150 degrees. Let's look at the next one, arc DGH. Arc DGH is an arc that begins at D, moves around towards G, and ends at H. We already know that from D to G, this is 150, and now we need to continue the rest of the way from G to H, which is another 120 degrees. So we want the 150 degrees that's from D to G, plus the 120 degrees from G to H, for a total of 270 degrees. Now let's look at our last one. Arc DH. Arc DH would be an arc that starts at D and ends at H. So it's the remainder of the circle. We already know that from D to G around to H, arc DGH, we have found was a total measure of 270 degrees. We want the remainder of the circle, DH. So we want the entire circle, 360, minus the 270 degrees that was arc DGH, to find arc DH, 90 degrees. Alright, let's look at a couple of postulates and theorems that we discussed last week. Remember that in the same circle, or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Remember, the if and only if statements are true forwards and backwards. In other words, two minor arcs are congruent if their corresponding chords are congruent. The converse of that is also true. We can go the other direction, and we can say that if two chords are congruent, if their arcs are congruent. So true forwards and backwards. Arc AB is congruent to BC if and only if chord AB is congruent to chord BC. So true forwards and backwards. If you know the chords are congruent, the arcs will be congruent. If you've given that the arcs are congruent, then the chords will be congruent. Let's look at the next theorem. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. To use this theorem, you must have a diameter. Remember, a diameter passes through the center of the circle, goes all the way across the circle, and passes through the center. If that diameter is perpendicular to the chord, then that diameter does two things. It bisects the chord so that ED will be congruent to EF, but it also bisects the arc so that arc DG will be congruent to arc FG. Okay? So, if a diameter is perpendicular to a chord, it bisects the chord and its arc so that segment DE and EF will be congruent, and arc DG and arc GF will be congruent. Let's look at the next theorem. If one chord is a perpendicular bisector of another chord, then the first chord is a diameter. This is the converse of the theorem that we just discussed. In this theorem, instead of knowing that this is the diameter, we're going to figure out that it is the diameter. Because we see that this chord is perpendicular to another chord, and we should also notice that the chord bisects this chord that it's perpendicular to. When a chord is perpendicular and bisects another chord, then that chord must be the diameter, which means it will pass through the center of the circle. If this is a diameter, then it cuts this into two semicircles. So, because this chord is the perpendicular bisector, JK is the perpendicular bisector of ML, and we know JK is the diameter of the circle. And I believe this is our last one. In the same circle, or in congruent circles, two chords are congruent. Again, we have this if and only if statement, meaning it's true forwards and backwards. Two chords are congruent if and only if they are equidistant from the center. Remember, this word equidistant means the same distance. So if two chords are the same distance from the center, then they are congruent. Okay? So if the distance EG is congruent to the distance GF, then the chord CD will be congruent to the chord AB. The converse to this is also true because it's an if and only if statement. Then we can go the other direction and say, if these chords are congruent, then these distances will have to be congruent. Okay? So we can say AB is congruent to CD if and only if, meaning we can go either direction, if and only if EG is congruent to EF. Alright, let's look at a couple of examples where we'll use what we've discussed, and then you can begin your homework. In this example, we want to find the measure of arc RS. RS is this arc right here, equal to 7x. So to be able to find what RS is equal to, we must know what x is equal to. We need to write an equation and solve for x. Notice that RT is the diameter of this circle, a diameter of this circle, since it passes through the center. We discussed in the theorems today that if a diameter was perpendicular to a chord, that diameter not only bisected the chord, but it also bisected the arc, which means it's cut this arc into two congruent pieces. So that arc RS is congruent to arc RV. Substitute in, you know arc RS is 7x, then it will be equal to arc RV, which is 3x plus 24. Subtract 3x from both sides, 4x will be equal to 24. Divide by 4, x will be equal to 6. Now this is just what x is equal to, but does not give us the final answer for what we were asked for. We were asked to find the measure of arc RS. Remember, arc RS is equal to 7 times x. We know that x is 6, so we now know that the measure of arc RS is equal to 7 times 6, or 42 degrees. Here's our final answer. Alright, let's look at the next example. In this example, we want to find segment HK. Segment HK is this distance from the center to the chord. We want to find HK if segment DG is equal to segment JL, and they are both equal to 24. So they're congruent to each other, and they are both equal to 24. So we know that DG is 24, and we know JL is 24. We also know that this segment DH is 13. Okay. Because the two chords DG and JL are congruent to each other, from theorems discussed in this lesson, we know that if two chords are congruent, then they are equidistant from the center, which would mean that HF is congruent to HK. We're being asked to find HK. If we knew HF, we would be able to find HK because they would be the same measure. Notice that using the piece DH they gave us, HF, and this segment DF, that we have a small right triangle. Because this segment HF is a part of a diameter, remember when a diameter is perpendicular to a chord, it bisects a chord, so this segment HF would be a portion of a diameter. Since it's perpendicular to this chord, then it bisects this chord and cuts it into two equal pieces. So this side would be 12, this side would be 12. Now I have a small right triangle here where I know two sides of the triangle and I want to find the third. The segment that's 13, that's our hypotenuse. Then it would be equal to a leg squared plus a leg squared. One of the legs there is HF. Simplified, 13 squared is 169. That would be equal to 12 squared, 144, plus HF squared. Subtract 144 from both sides, you would be left with 25 is equal to HF squared. Take the square root of both sides, so we want the square root of 25 is equal to HF. So 5 is equal to HF. Remember up here at the beginning we said that HF and HK were equal to each other. We were asked to find HK. Since HK is equal to HF and HF is 5, then HK is also 5. Alright, that's our lesson reviewed. You may now open your textbooks and begin your homework. Open your textbooks to page 607. Open your textbooks to page 607. Begin this assignment. It will be due tomorrow. See you tomorrow.